Okay, so now we will try to understand some physical mechanism of convection and some basics which are important for the pipe flow. So we already know from Newton's second law of cooling that the physical expressions for the convection mechanism is this phase delta T. So we know it for the convections, or this is you can say this is the heat flask. So what is heat flask? If we know Q dot, this is the rate of heat transfer. If we divide it by area, per unit area, then we'll get the heat flask. So you look here, the convection heat transfer, actually this is something that depends on a lot of things. It depends on the, you look at the dynamic viscosity, conductivity, density, the fluid properties, and the specific heats, fluid velocity, the geometrical parameters. So we'll discuss it later on. But here, just one thing, you look here, what do we need? We need the convection heat transfer coefficient. We need the surface area, heat transfer surface area, surface temperature, and the air temperature. So this is the formula we know. And you already know this is called the Newton's law of cooling. So when we will actually analyze, when we'll apply this convection heat transfer mechanism in pipe flow, so inside the pipe, let's say we have a pipe like this. So when there will be fluid flow inside the pipe, we need to know some new concept, the no-slip conditions, the boundary layer. So you already know, some of you already know what is the no-slip conditions. So you just look here, and for the boundary layer, we need some discussions. So I just put this definition here. You look here, and you can go through the books later on. So I will not discuss it here, but we will discuss it during the tutorials and lecture. So what I'm trying to explain here is the Reynolds number. This is non-dimensional, or you can say the dimensionless number that is related to the heat transfer coefficient, convection heat transfer coefficient. Look, this is the cross-sectional view of the pipe. The fluid is the fluid. This is the fluid layer. Okay. We know this temperature, outside temperature T2. This is T1. This is the rate of heat transfer, and this is the characteristics lengths. So we know from conduction. So here you see, we know the formula for conduction and convections. So when we are talking about the heat flask, that means you need to divide by area. So it will be, let's say, if the conduction is K, A delta T over L, and if you divide by A, so you can cancel out this. So it will be like this. This is the thermal conductivity, temperature difference, and thickness. Similarly for the convection, from previous slide. You just calculate the ratio of this convection and conduction. So you can see, you can cancel out this delta T and delta T. So it will be H L over A, the thermal conductivity. This is called the Reynolds number. So what I can say, the physical meaning of the physical meaning of the Reynolds number is that is actually the ratio of the the convection and the conductions. So you can say it is actually the convections, it's relative to conduction across the same fluid layer. So the Reynolds number definition, you just keep in mind, this is H L C over K. So this is the convection heat transfer coefficient. This is, thermal conductivity, and L is the characteristics length. This is the Reynolds number definition. So we will use this Reynolds number definitions again and again throughout the semester for when we will calculate the total rate of heat transfer, or the convection heat transfer coefficient. So what we can say from here, Reynolds number is H L C over K. So when we'll tell you, okay, calculate the convection heat transfer coefficient, then you can simply calculate the Reynolds number. So if you know the Reynolds number somehow, then you will be able to calculate this case. because this is the thermal conductivity, it is constant, and this is the characteristics length. So it will be given. So if you know Reynolds number, then you can calculate the thermal, the heat transfer coefficient. So what we'll know now is the Prandtl number. This is another non-dimensional number. This is here's the definition. I will not discuss a lot about it. So basically, the Prandtl number for gas, we say this is about 1, and which means you can see it is actually the molecular diffusivity of momentum and molecular diffusivity of heat. That means this two ratio is 1, so their ratio will be nearly the same. Heat diffuse very quickly for liquid metals and slowly for water. So we'll solve some problem where the materials will be water, maybe. So for water, generally this is constant 7.0, but we'll get some other values. We'll deal with different materials. So the Prandtl number for water, this is, we'll use it as 7.0, but we'll get some other materials and the corresponding Prandtl number. So if you ask me how you will get this Prandtl number, so you'll get it from the tables. Check the appendix and we'll discuss it during the tutorials. So then when we're talking about the pipe flow, this couple of things and the heat transfer, then all these things are important. Here is general assumptions. Look, what I really want to stress here is you need to consider the mean temperature. Why? Look, this is the temperature profile here. So this is the TS, the surface temperature, and you can see this is the temperature profile. So what we can say, if you look these arrows, then can we say the temperature? So if I say, okay, this arrow, it actually tells the magnitude as well. So the temperature magnitude. So if the arrow is long, it's high temperature. If it is short, low temperature. So we can say it is the minimum temperature here. And then temperature will increase if we go far from the center. So at this center point, temperature is minimum. If you go from this point to this point, like if you go far from the center, temperature will increase. So if you need to analyze a pipe where the temperature actually varies from center to left and right, then how you will actually analyze it? So for better accuracy, we will actually consider the mean temperature. So mean temperature means, let's say, this is the line. Let's say this is the mean temperature. So in other words, you can say it is the average temperature. How you can calculate it? Here is the formula. I will show you in the formula later on. So this is how you can calculate the mean temperature. But I will show you a very simple and easy, straightforward way to calculate the mean temperature. So this is some general formulas. And the Reynolds number, you are very familiar with these concepts. This actually tells when the flow will be laminar and turbulent. So you already know the Reynolds number definitions for the pipe flow. This is internal flow. So when the Reynolds number is less than 2300, okay, less than 2300, then we'll say it is laminar. If the Reynolds number is greater than 2300, at this point, transition starts, but usually there are some different opinions. So we can say this is turbulent. We can say at this point it is turbulent, or some people say it is transitional. Here it says greater than 10,000, it is fully turbulent. That means it is highly turbulent, kind of chaotic. So what I'm telling here, so just keep in mind only this information. If the Reynolds number is less than 2300, then we will say this is laminar flow. And the last thing is, the pipe flow. When you're talking about the pipe flow, there is another important concept we call the boundary layer. So we already know the concept of the boundary layer. So you can see here, actually, it's showing the boundary layer. And the flow at this case, you look at this point, this arrow, it is actually telling the fluid direction and the magnitude. That means at this point, all the fluid particles, they have the same magnitude, same velocity magnitude, okay? When it starts moving, so you will see here, at the center, the velocity magnitude is increasing. So you know this concept. So we already discussed it, because the fluid particles actually, hit the wall, and the wall is static. It's not moving. So at this point, it is zero velocity. So to maintain the continuity, so the velocity at the center particles, it increase. So you see now gradually, due to this viscous effect, we can see the layer, this is increasing like that. And at this point, you see now it becomes fully developed. So now after this point, it will not change anymore. So from here, it will be the same profile like this. So we know the entrance reason is the reason from the inlet or the entry, you can say from the inlet to the point where the fluid or the flow will be fully developed. So fully developed means it will becomes kind of this parabolic shape, and it will not change anymore. So you look here, this fluid, uh, this is, we can say, the flow is streamlined. So you see it is changing. It is changing up to this, and after this it will not change anymore. So at this point, we can say this is fully developed flow. Just keep in mind, fully developed flow means we'll say it is just a parabolic flow. So the flow, it will be constant. We'll get the maximum velocity at the center. You already know that. So up to this point, we'll say this is the entrance region, and this length, we will say the entry length. Entry length is the length where the flow will be fully developed. And we know basically the two boundary layer, they just intersect at this point. So we already know this, and we'll have more discussions during the tutorials. We really want to keep the video length as short as possible. So if you go through the books, then you will see different expressions for the entrance region, like when for laminar flow, for turbulent flow, how to calculate the entrance region or the entry length. So you will get it from the book, and we'll solve related problems later on. So from this video, what we learn is what is the entrance region and how we can calculate it. We just understand that, okay, for pipe flow, we'll analyze the system and we'll consider the mean temperature. We also learn the Reynolds number and the Reynolds number, and also we know, uh, you know, the general Newton's law of cooling. So this is all about from this video. In the next video, we'll try to understand, all the thermal considerations for the pipe flow.